Okay, we've got the 11 kilo rotor aluminium with 2 discs, and with the magnet housings, this one's got the bearing and the needle point, so it's probably about 15 kilos. We'll get some scales that we can weigh it, because it will send my kitchen scales around the clock 3 times, which don't think will be very good for the kitchen scales. This side's got nothing at the minute, that's just free floating. So you can see there's a little bit of wobble there, but we know the shaft is bent, and you can see that. Just like that, you can see the shaft's bowing. And you can see it wobbling, so if I go up close, that side and that side. So we're waiting on the 30mm shaft. We've taken the shaft off, and we've got the measurements all down on here, so that can be put into CAD for the new 30mm diameter, 800mm long shaft, stainless 316, polished and ground, so it'll be very true concentric shaft. So the engineering company's not long emailed me the hardened steel discs, which will go on the inside of there, can be fitted on just by putting them on, because of the magnets, they'll just stick on. So that means we can have a needle point touching either end, and there'll be even less friction than using these bearings. But as you can see, it's not running too bad. Considering this rotor isn't on a straight shaft, and it hasn't been balanced on the new shaft, and we haven't checked the concentricity of the magnet housings and balanced it with all that new equipment. We're not doing too bad really. Levitating a 15 kilo load is quite different to any other permanent magnetic bearing I've seen out there. I wonder how long it's run for. It's ran for 3 minutes. So over here we're working on the base and the big pump, which the permanent magnet bearing is going to be for. Can hear a bit of a wobble. Get a bit of a wobble on here, so it's hit a frequency that is causing a lot more vibration. It's sort of leveled out. So that's the state of play for the magnet. So you can see it's still quite a bit that side. That side is being stabilised by one of the Z-axis bearings. It's going to be wobbly again. We're going to do the same test in a minute, just with the bearing on this side as well. So we've got bearings on both sides, so you can see the stability of it then and the run time. We should have added a tachometer mark to the shaft as well, so we knew how fast it was going from. Also, we haven't double checked the distance from there to there, and the same on this side. Although the hub does stick out and take a bit more of the weight this side compared to that side. That side hasn't got the hub; it's just got the washers and the nuts. But this is just a dummy. This is just a dummy load to check the operation of the permanent magnetic bearing and to check the operation of the Z-axis and the stability. Knowing that the shaft is bent means that we can't expect anything amazing from this. So we're coming up to 6 minutes now. Obviously, the heavier the load that's levitated, the longer it's gonna spin without any input. Once up to a certain speed, it stands to reason that a 5 kilo load versus a 10 kilo load versus a 15 kilo load, the 15 kilo load, if all of three have been levitated, that the 15 kilo load will spin for considerably longer because of the inertia stored in the flywheel. And we just span this up by hand. We could have span it a lot more, but it seemed like it was good enough to make a video. So it's not completely contact free. It can be a lot better than this. Using the hardened steel discs and adjusting the Z-axis needle points. If we get it in the sweet spot, this will run for a very long time, particularly with a shaft that is true and concentric, because any vibration and wobble will rob energy. So we've gone into over 7 minutes now. See that little wobble. We put a straight edge against the shaft when it was all apart, and you could clearly see a deviation, that the shaft wasn't, the threads weren't perfectly straight. So it's not too noisy either, really. Although obviously the noise will increase with the RPM. Just a little bit closer today. Let's see. We've got the Z-axis adjuster there. We've modified the washers this side so we can get this triple arrangement there, and same on this side. So ultimately, bringing in these two magnets and having magnets like there would significantly increase the stability. Surrounding it with adjustable magnets would definitely improve the stability, but the main thing to improve the stability right now is to get the polished and ground shaft, and that's going to be a game changer. You put significantly less load on the bearing, and there's nothing really to steal the energy then other than air friction. So we've gone into 9 minutes, and yeah, it's looking good. So looking forward to receiving this new shaft. It should arrive on Monday. and the design is almost done. So it's having another little moment now because of the bent shaft. So having magnets that completely surround the magnet in this housing wouldn't allow that side-to-side movement, and the closer that these magnets can be brought into this magnet, the stiffer the bearing. And if you can make a permanent magnetic bearing that's stiff enough, it is possible that a magnet could repel the magnet that's in here. We'd need one on this side and this side, and then if we could repel it from all directions, then this rotor will be literally floating in thin air. And if it runs for this long off a hand spin with a contact point, and there's 11 balls in those bearings, so there's plenty of contact points, it will run for considerably longer. All of this is on the way to making a self-propelled windmill or wind turbine in a box, and it will do that from the viscosity and adhesion of the air. As this rotates in the box, it will make a vacuum, and that vacuum, the negative pressure, will make atmospheric pressure rush in and impart the weight to the rotor as it exits, and that weight will lever this rotor round and round, exacerbating the situation, which will increase the vacuum and bring more air in. So actions speak louder than words. Let's get this permanent magnetic bearing fully ready to go in the big vacuum pump, and then we can put our money where our mouth is. So 12 minutes we're into now. The rotor is made from aluminium 5083, I believe. The hub there is made by Dunlop, or Medway, which is a subsidiary, and they're about £15. The taper lock bush, which is silver there, about £6. That's a 19mm taper lock bush. The biggest you can go on this particular hub, which is a 1210 Dunlop, is 32mm. We're going for a 30mm shaft, just because that was what was available off the shelf, and the next size up was 40mm, which is a bit too big. So the new shaft will have threaded ends which will go into the magnet housings, and we can thread lock them on for a final piece before balancing. The magnet housing here is going to have a couple of notches put on so that it can be tightened with a spanner, or removed with a spanner. And all the fixings on this side, these are all 316. 316 is probably the cheapest, least magnetic metal. I did price up some discs this size. It was a 2 metre by 1 metre sheet of one of them was titanium, grade 5, aerospace grade. Another one was a nickel alloy, and the nickel alloy one was about £3 for a 2 metre by 1 metre sheet, which is a lot of money. The titanium was 1,800, which is also a lot of money. And also there was a middle price, which was Inconel 910, I think it is, and that was kind of about £2.5 grand. So big money for a 4mm sheet. This being 4mm, this rotor did warp at around 489 miles per hour periphery speed, which was 5,200 RPM for an 800mm rotor. And the rotor still is warped together, so it's actually gone from two perpendicular discs into the shape of two cymbals, like a UFO sort of thing. And the strange thing is, if you take this up to 2,000 RPM, the centrifugal force actually pushes the two discs apart. This would explain why Tesla later moved on to having star washers that were had fingers that kind of let the discs space out, but also having bosses or protuberances or rivets that would push the discs apart. And he obviously experienced this. And the solutions are either going for a higher tensile material or having the bosses, rivets or protuberances, which can be pressed, or you could actually weld or machine and screw any of that stuff on a big rotor like this. Small rotors, best to press it in. So we're into like 16.5 minutes now, and that was the compressor. So yeah, it looks like it's not got too much run time left. Yeah, another solution for preventing warping would be to have thicker discs. These are 4mm, and not a particularly high tensile grade of aluminium, sort of a run over the mill, because it was just for an experiment. And previously I was using mild steel, which the same size rotor is 27 kilos, whereas this one's 11 plus the magnet ends, which are about 2 each, so it's about 15 kilos. Don't think this magnet setup we've got will hold 27 kilo. We might give it a go a bit later. But yeah, titanium's heavier than aluminium, but significantly higher tensile. Another solution would be aircraft grade 7075 T6 aluminium, which is aircraft grade aluminium. That would work well, I'm sure. And if these are 4mm sheets, then we could go to 5mm and put some around the edges. So like at least 3 places at a minimum, if not 6 or 9. It could be 4 or 8. Just anything to keep the disc spacing apart, because you're losing surface area until it gets to a certain speed with it warped like this. I mean, this is the first time I've shown this rotor since it was warped. Just gone over 18.5 minutes. It looks like it's about to stop any second. So yeah, that was an interesting demonstration of the new permanent magnetic bearing setup, and I think it proves that we're definitely going in the right way. Right, let's see how many times it goes back the opposite way, which is a trait. You can also see the bit where it was balanced, just there. That's this rotor was balanced to 10,000 RPM. Supersonic is 8,200. So you can always see how contact-free a bearing is by its ability to rock backwards and forwards. It's looking like it's showing us that is still the heavy spot. maybe not. So the next thing we're going to do, get the proper shaft, get it machined, test it on this rotor. We're also going to test the 27 kilo rotor to see if this assembly is powerful enough to levitate that. Also working on a much simpler apparatus that will fit into this assembly. That should be quite interesting. More on that later. So still rocking backwards and forwards into 20 minutes, 20 and a half minutes now. Right, I'm going to call it a day there, folks. Thanks for listening.